Welcome to What If, where the possibilities truly are real and endless. What if the air we breathe could hold the key to ending plastic pollution and transforming our future?
Okay, everyone, I'm sure we've all had that feeling.
Yeah.
Like drowning in plastic waste.
Yeah.
You know,
Absolutely.
Every solution feels like just a tiny
Right.
drop in the ocean.
Right. It's a big problem.
Yeah. And it can be so overwhelming trying to
Yeah.
figure out what's really progress and what's
Right.
just wishful thinking.
I completely agree.
So what if there was a way
Uh-huh.
to tackle those mountains of plastic?
Okay.
The PD plastic.
Yeah.
Specifically, the kind they use in like most drink bottles.
Right.
But with something surprisingly simple.
Interesting.
Yeah, so we've been looking at some really fascinating research
Okay.
out of Northwestern University,
And?
a team led by research assistant Professor Yossi Kradish
Okay.
and Professor Tobin J. Marks.
Uh-huh.
They've developed this new method to break down PT plastics using a catalyst and get just the moisture in the air.
Wow. That's impressive.
For anyone who's felt lost in the complexities of
Yeah.
current recycling, this feels like a potential
Yeah.
game changer.
For sure.
So our deep dive today isn't just about the science, though.
Okay.
We're going to really explore the most
Yeah.
unusual, different, even a little bit off-the-wall possibilities this breakthrough could unleash.
I like it.
So before we get to the exciting what-ifs,
Yeah.
let's quickly kind of recap why this new approach is so significant.
Mm-hmm.
Traditional peat recycling isn't exactly a smooth operation, right?
Well, it's important to understand the limitations of how we currently recycle PE.
Okay.
It often requires really high temperatures and these really harsh chemical solvents.
Okay.
And that requires a lot of energy.
Yeah.
And even with all that effort,
Yeah.
the recycled plastic is often downcycled.
Downcycled.
Yeah, think of it as a downgrade.
Uh-huh.
Like a plastic bottle might become something like carpet fibers,
Oh, God.
which then can't be recycled again.
I see.
So it's not really that closed loop system that we're aiming for.
So it's more of a
Yeah.
single detour than a true
Precisely.
return trip for the plastic.
Exactly. Okay.
So how does this Northwestern method sidestep those, energy-intensive
Right.
and chemical-heavy steps?
Well, the beauty here is really in the simplicity of it.
Okay.
Right off the bat, it's a solvent-free process,
Oh, wow.
which is a huge win for the environment.
Okay.
The main players here are a molybdenum catalyst
Uh-huh.
and activated carbon.
Okay.
And these aren't rare or toxic materials, which is a
Okay.
big plus.
Yeah.
So the process starts by combining the PET with this catalyst
Uh-huh.
and applying some heat
Okay.
to start breaking down those long plastic chains.
Oh, I see.
So think of the molybdenum catalyst as the key
Uh-huh.
that unlocks the plastic's bonds,
Okay.
and the activated carbon is like a support structure
Uh-huh.
that helps the reaction happen efficiently.
Okay. So heat and a catalyst to get things
Exactly.
started.
Yeah.
But the real magic seems to be in what happens next.
Yes.
The air-powered part.
Right.
So tell us about that.
This is where it gets really interesting.
Okay.
After that initial breakdown,
Wow.
the resulting fragments are exposed to just ordinary air
Okay.
with its natural humidity.
Okay.
And this moisture triggers a really critical chemical reaction.
Uh-huh.
And it converts those fragments into terephthalic acid,
Terephthalic acid.
or TPA.
Okay. TPA.
And this TPA is essentially the raw material
Right.
that's used to make new PE plastic.
Oh, wow.
So the process breaks down the old plastic
Perfect.
into its original building blocks,
Yeah.
ready to be used again.
So it's maintaining that quality and closing that loop.
Exactly.
Wow. Just using moisture from the air. That's the real
Oh, it's amazing.
aha moment for me.
Yeah.
And the research mentioned some pretty impressive results.
Oh, yeah, absolutely.
Didn't it?
They achieved a 94% recovery rate of TPA
94%.
in just 4 hours.
That's incredible.
That's a near perfect loop
Yeah.
in just hours.
Wow.
Compared to these energy-intensive processes that often yield much lower-grade materials.
Yeah.
And what's also remarkable is that this process
Yeah.
can handle mixed and even colored plastics
Oh, wow.
without needing to sort them.
That's huge.
If you've ever stood in front of a recycling bin confused,
Oh, yeah.
you'll appreciate what a massive hurdle that is.
Absolutely. So this has huge practical implications.
Yeah,
But we're here to go deeper,
let's do it.
to explore the truly unusual possibilities.
Okay.
So let's start with the environment.
All right.
So we can envision less landfill waste and cleaner oceans, which is
Of course.
fantastic.
All right.
But what are some of the really out there environmental scenarios this could lead to?
Well, this incredibly efficient process, naturally leads us to consider the huge impact it could have on the environment beyond just the obvious things you mentioned.
Right.
The research points to a potential dramatic decrease in plastic pollution.
Right.
But let's really speculate here.
Yeah.
Could we envision a future where this catalytic principle inspires the development of these specialized, perhaps even airborne catalysts?
Airborne.
Yeah, designed to target and break down existing plastic pollution in specific environments.
Like how?
Imagine drone-deployed catalysts neutralizing plastic patches in the ocean.
Okay.
Or even in a far-off scenario,
Yeah.
engineered systems that could tackle microplastics in the atmosphere.
In the atmosphere. Wow.
It sounds like science fiction now.
Yeah.
But the fundamental idea of using a catalyst
Right.
and ambient conditions to degrade plastic is there.
That's true.
Of course, we also need to be mindful of unintended consequences.
Yeah.
Large-scale deployment of any new technology could have unforeseen byproducts or ecological impacts that we can't predict.
Airborne plastic-eating catalysts. That's the concept.
I know, it's pretty wild.
Right out of a movie.
Yeah.
Okay, so now let's turn to the economy. The research hints at a potential boom in the recycling sector. But what are some of the more unexpected economic shifts we might see?
Well, if we connect this near-perfect recycling loop
Okay.
to the bigger picture of resource management, things could get really transformative.
Okay.
The research suggests lower production costs for new PPA.
Right.
But what if the value of recycled TPA becomes so high,
Yeah.
thanks to this efficient process, that it fundamentally reshapes entire industries?
Wow.
Imagine a future where recycled TPA becomes a major global commodity, like oil or metals,
Wow.
with its price influencing stock markets
That-
and international trade agreements.
Yeah.
We might even see the rise of these specialized plastic refineries
Plastic refining.
that do nothing but process old plastic into valuable TPA.
Wow.
On the flip side, this could obviously disrupt traditional petrochemical companies
Right.
that rely on producing new plastic from raw materials, potentially leading to some significant economic restructuring and job displacement in those sectors.
So from waste to wealth, literally trading in trash.
Exactly.
On a global scale.
Yeah.
What about the social and cultural changes?
Okay.
A greater sense of environmental responsibility seems likely, as the research suggests.
Okay.
But could this technology spark any truly unusual shifts
That's a great question.
in how we live our lives?
What's fascinating here is the potential for a real democratization of recycling.
Democratization of recycling.
Yeah. Picture a future where compact, highly efficient home recycling units,
Home recycling units.
based on this catalyst and air moisture principle,
Wow.
become commonplace. Instead of just sorting our waste, we might have devices that break down our plastic packaging
In our homes.
right in our kitchens.
Wow.
Could this lead to a fundamental shift in how we perceive waste?
Oh, that's interesting.
Moving from something to be discarded to a valuable personal resource.
Right, like a commodity almost.
Exactly.
Yeah.
Perhaps we'll see a surge in local small-scale manufacturing
Hey.
with individuals using recycled materials as the feedstock
Yeah, wow.
for 3D printers or other personal fabrication tools,
Interesting.
fostering a true circular economy at the household level.
That's fascinating.
However, the ease of such efficient recycling could also lead to a paradoxical effect.
Okay.
If we believe that all our plastic is being perfectly recycled at home,
Right.
we might become less motivated to reduce our overall consumption.
Of single-use plastics in the first place.
Exactly.
So home-based recycling factories, that's a
It is a pretty wild thought.
fascinating thought. It could completely change
Yeah,
our relationship with the stuff we use every day.
for sure.
Now let's consider other technological innovations.
All right.
The research indicates this could inspire further breakthroughs
Yeah,
in recycling.
definitely.
Where might that lead us in truly unexpected directions?
Well, this research really opens the door to applying this air moisture activation principle
Okay.
to breaking down other notoriously difficult materials.
Other materials, not just
PT.
plastic.
PT is just one type of plastic.
Right.
Imagine if we could develop similar catalysts that, when exposed to specific atmospheric components, not just moisture, but perhaps other naturally occurring gases, could efficiently decompose complex materials, like electronic waste, breaking down circuit boards into their constituent metals and plastics. Or even certain types of composite materials used in construction. We might even see the development of products designed for self-demolition at the end of their lifespan.
What does that mean?
Imagine packaging that safely degrades into harmless components simply by being left out in the rain.
Wow, so it just breaks down on its own?
Exactly.
That's amazing.
Of course, a major hurdle would be ensuring the stability and longevity of these materials during their intended use.
Of course, we don't want our smartphones dissolving in our pockets.
Exactly. Also, the reliance on specific catalysts could create new supply chain vulnerabilities. If those materials become scarce, or if their production has significant environmental costs.
That's a good point. Self-destructing gadgets. That would certainly make e-waste.
It would be a
thing of the past.
A game changer.
Okay, what about the geopolitical landscape? The research touches on countries leading in sustainable technology, gaining influence. Could there be even more surprising geopolitical ramifications?
Well, if we consider the immense scale of global plastic waste and the potential economic value in efficiently recycling it, access to and control of these advanced recycling technologies could become a significant source of international power and influence. Yeah, nations that master these technologies could offer solutions to countries struggling with massive waste management issues, potentially creating new dependencies or alliances.
So you're saying it could be a bargaining chip?
In a way, yes.
Interesting.
We might even see international collaborations focused on establishing global standards and infrastructure
for this new type of recycling.
Exactly. Conversely, if the technology remains concentrated in a few developed nations, it could exacerbate existing inequalities, leaving developing countries still burdened by plastic waste.
Without the means to process it.
Exactly.
So waste management becomes a new form of global leverage.
It's a very interesting and potentially concerning perspective.
It is. Okay, now let's really push the boundaries here.
All right.
And think about some truly outlandish possibilities.
Let's do it.
Beyond what the research directly suggests, what about the concept of self-sustaining cities? The research mentions waste to energy. But can we take that much further?
Let's envision a future where open centers evolve into truly circular ecosystems.
Circular ecosystems.
Yeah, imagine integrated systems powered by this efficient catalytic breakdown of waste that not only provide energy, but also extract valuable raw materials.
From the discarded products.
Exactly.
In surprisingly efficient ways.
Maybe we could see these localized urban material recovery centers.
Urban material recovery centers.
Yeah, that become key hubs for resource regeneration. Almost like modern-day alchemy, transforming waste into the building blocks for new industries within the city itself.
So the city is providing its own resources from its own waste.
Precisely.
Wow.
Maybe even rare earth elements.
Okay.
Currently difficult and environmentally damaging to mine could be recovered as byproducts
of this process.
Of these advanced recycling processes within our cities.
That's incredible. So urban centers as resource powerhouses, that's a radical reimagining of city infrastructure.
It is.
What about space exploration? The research notes the potential for reducing supply needs, which is vital for long-term missions.
Absolutely.
But what other doors could this technology open in space?
Think about the incredible logistical challenges of establishing a long-term human presence beyond Earth. Transporting vast quantities of materials is a major limiting factor. Now, imagine being able to utilize locally available resources on other planets. The regolith on Mars, for example.
The Martian soil.
Exactly. And combine it with recycled plastics brought from Earth. Or even waste generated during the mission and process it with minimal energy using this type of catalytic technology.
Wow.
Could we potentially 3D print habitats.
3D print habitats on Mars.
On Mars, yeah.
Wow.
Create radiation shielding or even manufacture tools and scientific equipment on site.
Wow.
Significantly reducing our reliance on Earth-based resupply missions.
Right.
And paving the way for truly self-sufficient extraterrestrial settlements.
Building Martian colonies from recycled water bottles and Martian dust.
I know, it's mind-boggling.
It is. The possibilities are mind-boggling.
They are.
And what about integrating this into the natural world, biological integration?
Oh, that's a fascinating area.
The research touches on engineered organisms.
Right.
Can we take that concept to an even more unexpected level?
Let's really think outside the box here.
Okay.
What if we could bioengineer not just microorganisms,
Yeah.
but even plants or fungi?
Plants or fungi.
Yeah.
No.
To naturally produce this type of catalyst within their structures.
Wow.
Or as part of their metabolic processes.
Yeah.
Imagine planting specialized vegetation in areas heavily contaminated with plastic,
Right.
where these organisms passively secrete the catalyst, leading to this widespread natural breakdown of plastic pollution over time.
That's incredible.
It is.
So it's like self-healing ecosystem.
Exactly.
Wow.
Of course, we'd need to carefully consider the ecological implications and ensure that these engineered organisms don't disrupt existing ecosystems
Of course.
in unforeseen ways.
Right.
It's a powerful but potentially complex approach to environmental remediation.
Imagine forests that naturally decompose plastic. That's a truly
It is.
transformative vision.
Yeah.
Finally, let's revisit the idea of an economic paradigm shift.
Okay.
Waste futures are already intriguing,
Yeah.
but could we see even more fundamental changes
Absolutely.
to our economic models?
Let's consider the incentives.
Okay.
If waste, particularly plastic waste, becomes a truly valuable and easily recoverable resource,
Right?
could we see the emergence of entirely new economic models
Wow.
centered around resource recovery and reuse?
Okay.
Imagine a system where individuals and communities are incentivized,
Okay.
perhaps through direct payments or tax benefits.
To collect and process plastic waste on a very local scale,
Wow.
using small, accessible versions of this technology.
So you're saying like a micro-recycling industry almost?
Exactly.
Wow.
This could create new forms of decentralized economies,
Interesting.
empowering communities,
Yeah.
and potentially reducing our reliance on these traditional linear models of production and consumption.
Yeah.
Waste could truly become a currency in a circular economy.
So from self-healing ecosystems to economies built on reclaimed resources,
Yeah.
this seemingly simple scientific breakthrough
I know.
really does open up a universe of possibilities.
It does.
Some incredibly exciting,
Yes.
others perhaps a little unsettling.
Right.
It certainly makes you look at that plastic bottle
It does.
in your hand in a whole new light.
For sure.
It really does.
This research out of Northwestern
Yeah.
offers a potentially revolutionary pathway towards a truly circular economy for plastics.
Right. And the implications ripple far beyond just our recycling bins.
And with that, here's a final, perhaps slightly outlandish thought for you.
Okay.
If we could so effectively transform one of our most persistent pollutants
Right?
with something as commonplace as air,
Yeah.
what other seemingly insurmountable challenges
Right.
might hold equally surprising and elegant solutions,
It's a great question.
waiting to be discovered
Yeah.
in the most unexpected places?
Exactly.
Think about that. Not just for plastics,
Right.
but for any complex problem you can imagine.
I love it.
You might just surprise yourself with the possibilities.
Absolutely.
Thanks for listening.
Thanks for having me.
Our podcast, AI Voices, are courtesy of Notebook LM and 11 Labs, the humans and AIs of the AI Plus Roundtable. Thank you for joining us on this journey into uncharted territories.
Visit us on Substack at airoad.substack.com for free access to our other expeditions into the unknown. We thank our producers, the humans at Innovation Toronto and ChatGPT, Claude, Cohere, Copilot, DeepSeek, 11 Labs, Gemini, Grok, Llama, Mistral, Notebook LM, and Perplexity for co-creating the research used to create this podcast. We look forward to welcoming you on board. for our next explorations into uncharted territories.